We talked about moments, and next we will look at characteristic function and other transforms. First, we will define what the characteristic function is. The characteristic function is defined in this way. It's denoted by phi sub x or phi sub the random variable name. And you see, it's not a function of x, it's a function of omega. Okay, and by definition, it's the expected value of this function of random variable x, e to the power j omega x. And here maybe I should remind you that j is the imaginary unit, square root of minus 1. Okay, so this essentially is in general a complex function. It may not be real. And of course, in detail, we can formulate this for discrete random variables. We have the expected value of this function as summation over all possible outcomes, e to the power j omega k. K here is the outcome, each outcome, weighted by the corresponding probability at k. And for continuous distributions over the entire real line, the function e to the power j omega x weighted by the PDF and integrated over the entire real line. Well, if you have studied signals and systems, you should see that this resembles the Fourier transform a lot. This is the reason I mentioned that you need to know Fourier transform and related transforms in the first week, but you don't actually need to actually know it before. What we are going to do in this class, I'm going to give you sufficient detail, and but it's worth mentioning that the characteristic function and the Fourier transform of the PDF is very, very closely related. In fact, the characteristic function is the Fourier transform of the PDF, but the parameter is negated, the PDF of minus x, because in the Fourier transform, you would see a negative in the exponent. So this means all properties of the Fourier transform applies to the characteristic function. And not only that, but as you see, a fundamental property of the Fourier transform, it is invertible. Okay, when you have the function, you can obtain its Fourier transform, but it's a one-to-one relationship. It's unique. If you have the Fourier transform, you can recover the original function. So this is what we have. It's invertible. Therefore, for discrete random variables, you can obtain the PMF. For continuous distributions, you can obtain the PDF by applying the inverse Fourier transform to the characteristic function, okay, which is given here. You have a normalizing multiplier here, 1 over 2 pi, and here in the integral, you have in the exponent, you have a minus sign, okay? And now, how is this useful? What do we use the characteristic function for? In this week's class, I'm going to show you how to use it to compute moments, but it's not the only use case. We are going to use it for computing distributions later on. But just for today, for this week, we are going to focus on how to compute moments using these transforms, the characteristic function and others. For this purpose, we have to actually make use of the Taylor series expansion of the function e to the power x. The Taylor series is given here, the sum from k equals 0 to infinity, x to the power k divided by k factorial. This gives you the function e to the power x. Okay, so when you write the characteristic function of random variable x, what you get is, well, this, and here you have the exponential function. Just instead of this, put the Taylor series expansion, this here, okay? And then since summation and integration are both linear, I can exchange them as the variables permit. So I can pull the summation outside, but of course I cannot pull x outside because x, well, it's the integration parameter, so it has to stay inside the integral. But j, omega, and k can leave the integration because, well, just x is required inside. So this is what we have. But you see this integral here is what? It's the kth moment. Okay, so if you expand this expression, you get 1 for k equals 0. And when you put k equals 1, you get j omega times expected value of x. Plus, when you put k equals 2, you get j omega squared divided by 2, which is actually 2 factorial, times the second moment. Plus, for k equals 3, you get j omega cubed over 3 factorial times the third moment, and so on. It goes on like that ad infinitum. Okay. Therefore, what you have here is if you differentiate this expression with respect to omega, you get, well, this disappears, and here you get this omega disappears. You get just j times expected value of x plus something here that depends on omega. Here you see we do not have any omega. That means if you just plug in omega equals 0 here, you get rid of this term. What remains is just this, okay? So just take the first derivative of the characteristic function and plug in omega equals 0, you get j times the expected value. So whatever you get, divided it by j to obtain the mean value. Similarly, you get the nth derivative of the characteristic function. What you get is, well, the terms with, let's say, degree up to n will disappear, and you will get j to the power n times the nth moment plus a function in terms of w, omega, sorry. And when you just plug in omega equals 0, this disappears, okay, because it would have omega, omega square, omega cube, etc. So those will all go to 0. You will just have this. So take the nth derivative, plug in omega equals 0. What you get is j to the power n times, well, this should be nth moment. Okay, so this is how you can compute moments using the characteristic function.